Welcome to your first formal analysis course. Let's call this explainer your official initiation. Today, we're going to completely dismantle that intuitive understanding of numbers you've been carrying around, and we're going to rebuild it from the ground up using rigorous mathematical language. You know the math you've learned so far? It's relied pretty heavily on a kind of permissive, fuzzy intuition. But starting right now, we are transitioning to strict, axiomatic exactness. So let's jump right into the source material and see exactly how this is done.
Our text hits us immediately with this fantastic statement: no serious analysis is possible in a conceptual vacuum. We really have to start by shattering this illusion that the calculus you already know, the derivatives, the integrals, the limits, is just self-evident or historically sound exactly the way it was first taught to you. Relying just on your gut intuition, it's actually super deceptive. These objects were hard-won through literally 2 centuries of mathematical clarification. We desperately need exact formulations, heavily controlled proof patterns, and strictly defined objects. Think of this explainer as your basic survival syllabus for real analysis. Here is our roadmap. First, the conceptual vacuum. Second, the grammar of logic. Third, the quantifier trap. Fourth, methods of proof. Fifth, the crisis of intuition. And finally, axiomatic foundations.
Section 1, the conceptual vacuum. Section 2, the grammar of logic.
So why exactly do we have to abandon that comfy, familiar numerical landscape for exact formulations? Well, it's because in modern mathematics, we treat objects based on their structural relations, not just some vague picture we hold in our heads. To actually discover mathematical truth, we have to build a highly disciplined vocabulary, and that starts with our absolute baseline, the proposition. Simply put, a proposition is a declarative sentence that is definitively true or false, like 2 + 2 = 4, that's a proposition. But an open expression like x is greater than 0, that's actually completely meaningless on its own. It is not a proposition until we bind that x with a quantifier or plug in a specific value. Now, I know that sounds like a super pedantic distinction, but I promise you, it's absolutely critical. Literally every epsilon delta definition you're ever going to encounter in analysis is just an open expression that gets turned into a proposition by the exact quantifiers we place in front of it. When we map out the 5 primary logical connectives, it reveals something really fascinating, especially when we look at the implication column. Notice how it completely strips away physical causality? See, in everyday ordinary language, if I say, well, if the pavement is wet, then it rained, I'm implying a real physical temporal connection, right? But formal logic strips that away entirely. In math, if P then Q simply means the truth of P carries the truth of Q along with it. That's the whole shebang, nothing more. So if P is actually false, the implication itself is still logically true because it isn't making any further demands.
Section 3, the quantifier trap. Okay, real analysis is absolutely saturated with quantified statements. And I gotta tell you, one of the most common characteristic errors for beginning analysts is misreading the exact order of these quantifiers. Let's look at these 2 assertions. Over on the left, we have, for every epsilon greater than 0, there exists n. And on the right, there exists n such that for every epsilon greater than 0. Now, to the untrained eye, these might look superficially identical. It just seems like a stylistic shuffle of words, right? But mathematically speaking, they are violently opposed. And this brilliantly illustrates exactly why that is. If you put the existential quantifier first, there exists n. You are demanding a single magical n that works simultaneously for all possible epsilon tolerances. And honestly, that is a dramatically stronger and generically false condition. The correct standard for convergence puts the universal quantifier first, for every epsilon. What that does is allow our n to depend dynamically on the specific epsilon we happen to choose. The difference between these 2 orderings is literally the difference between convergence and non-convergence. And, negation is equally tricky. When taking the exact formal negation of convergence, notice how every single quantifier flips its type. For every turns into there exists, and there exists flips to for every. This is a huge takeaway for us. If you can't accurately negate a multi-quantifier statement by reversing each type and negating the core logical connective, then you really can't say you understand what non-convergence means in the first place. Section 4, methods of proof. All right, now that we've got our strict grammar down, we need to learn how to actually wield our arsenal. Because the choice of proof, it's never just arbitrary. A direct proof transparently assumes P to derive Q. Simple enough. But consider the contrapositive, assuming not Q to derive not P. Since P implies Q is completely logically equivalent to not Q implies not P, you really want to choose the contrapositive whenever the failure of the conclusion is just easier to analyze than the starting hypothesis itself. A classic example. To prove if n squared is even, then n is even. It is vastly easier to just prove the contrapositive. If n is odd, then n squared is odd. Then, of course, we have proof by contradiction. This is an incredibly powerful tool where we deliberately assume a statement is false just to derive a logical impossibility. But a quick warning here. You should reserve this for specific situations where direct proof is just totally hidden from view. The absolute classic example is proving the irrationality of the square root of 2. If you assume it can be written as a perfect rational fraction, it quickly leads to this glorious logical impossibility, exposing a deep inconsistency that no constructive approach could ever reveal so elegantly. And finally, mathematical induction. When beginners see this applied to, say, the sum of odd integers, a lot of them think induction is just some sort of trick, or worse, circular reasoning. I promise you, it is not. It is a direct, rigorous consequence of the well-ordered character of the natural numbers, which is basically the principle that every non-empty subset of natural numbers has a least element. You just establish a solid base case, and then mathematically prove that if it holds for k, it absolutely must hold for k plus 1.
Section 5. The crisis of intuition.
Okay, we have reached the climax. This is the exact historical moment where naive mathematical intuition literally breaks. See, for years, early set theory relied on this very permissive intuition known as unrestricted comprehension. That was the idea that if you could describe a property in words, you could just form a set out of all the objects that have that property. Sounds totally great, right? Well, it did, right up until we hit the famous Russell's paradox in 1901. Suppose we decide to create a set called R, which consists of all sets that are not members of themselves. Now we ask one really simple question. Does the set R belong to itself? Think about it. If R does belong to R, then according to its own definition, it shouldn't. But if R does not belong to R, then it perfectly fits the definition, so it absolutely must. If it does, it doesn't. And if it doesn't, it does. This is a catastrophic logical loop. It's a total meltdown, and the fault lies entirely in the permissive, fuzzy intuition of naive set theory. It showed the math world that to survive, we had to establish incredibly strict rules.
Section 6. Axiomatic foundations.
To save mathematics from these reality-breaking paradoxes, we had to introduce some very rigid guardrails. Think of basic set operations, like union, intersection, difference, and complement, as visual metaphors for our new, highly restricted universe. These operations act as our administrative machinery. They map out the safe, strictly defined boundaries within which we can actually trust our analytic arguments to hold up and not just collapse into contradiction. So instead of letting you naively create any wild collection you can dream up in your head, formal axiomatic set theory, specifically the Zermelo-Franco rules, steps in to provide an exact, highly limited list of permissions. You want to make a set? Okay, but you have to justify it. You have to use extensionality or the power set axiom, the axiom of choice, or one of the other specific rules. It takes that dangerous, unrestricted comprehension and completely replaces it with safe, structural relations. So, look at what we've done today. We've dismantled that naive intuition. We established the strict grammar of logic, we learned how to survive the quantifier trap, and we've completely secured our mathematical world with axiomatic set theory. But this leaves us with one final, incredibly provocative thought. Now that we have all this strict, heavy machinery in place, how do we actually use it to mathematically construct the real number line completely from scratch? How do we cure the geometric inadequacies of simple fractions? Well, that is a profound question, and it perfectly sets the stage for our next chapter, where we're going to build the real numbers out of nothing but pure logic. Stay curious, review those quantifiers, and I'll see you in the next explainer.